Heat of hydrogenation and resonance in benzene. Objectives: to study hydrogenation in unsaturated compounds, heat of hydrogenation and resonance energy in benzene, relation between resonance energy and stability in benzene, hydrogenation in unsaturated compounds. Addition of hydrogen to unsaturated hydrocarbons is called hydrogenation. This addition takes place in two different compounds, such as acyclic and cyclic compounds. Acyclic unsaturated hydrocarbons, such as ethene, on hydrogenation, form saturated hydrocarbon ethane. Similarly, cyclic unsaturated hydrocarbons, such as benzene, on hydrogenation, give cyclic saturated alkane cyclohexane. Both these reactions are exothermic. Heat released during these reactions is called heat of hydrogenation, and it is defined as the heat released when 1 mole of an unsaturated hydrocarbon is completely hydrogenated to a saturated hydrocarbon. Heat of hydrogenation and resonance energy in benzene. Heat of hydrogenation depends on the amount of unsaturation in the compound. For example, cyclohexene containing 1 double bond has heat of hydrogenation 28.6 kilocalories per mole, whereas cyclohexadiene containing 2 double bonds has 28.6 into 2, which is equal to 57.2 kilocalories per mole, as its heat of hydrogenation. While in a compound like benzene, which has 3 double bonds, its heat of hydrogenation should be 28.6 into 3, that is equal to 85.8 kilocalories per mole. However, the experimental heat of hydrogenation for benzene is found to be 49.8 kilocalories per mole. This value is 36 kilocalories per mole less than the theoretical value of a compound containing 3 separate double bonds. This value, that is 36 kilocalories per mole, is called resonance energy of benzene. Thus, resonance energy is the difference between theoretical and experimental heat of hydrogenation. Relation between resonance energy and stability in benzene. The resonance energy associated with benzene is due to delocalization of pi electrons in it. Benzene is a planar hexagonal molecule. To understand the delocalization in benzene, let us take a look at the carbon atom in benzene. Every carbon in benzene has 3 sp2 hybrid orbitals arranged at 120 degrees. 2 of these sp2 orbitals overlap with adjacent carbon atoms to form sp2-sp2 sigma bonds. Formation of 6 such sigma bonds results in hexagonal ring of the compound. The third sp2 orbital overlaps with 1 s orbital of hydrogen to form sp2s sigma bond. This results in a planar hexagonal C6H6 benzene ring. Each carbon of this hexagon has an unused pz orbital containing 1 electron. These orbitals arrange themselves perpendicular to the plane of hexagon. pz orbital of any one carbon atom can overlap with adjacent carbon atom located to its right or left side in the ring, as all of them are equidistant to each other. Consequently, 6 electrons in these pz orbitals extend over several adjacent atoms around the ring and are not associated with any single atom or a covalent bond. Such electrons are called delocalized electrons. Owing to delocalization of pi electrons, each of these bonds is neither a single bond nor a double bond. This can be graphically represented by a ring and is called a resonance structure. Greater the spread of charge over a molecule or ion, greater is the stability of that molecule or ion. Hence, delocalization in benzene gives it a greater degree of stability than if it had 3 separate double bonds. Summary. To conclude, we have seen hydrogenation in acyclic and cyclic unsaturated compounds to give saturated compounds. The resonance energy of benzene is 36 kilocalories per mole. Benzene contains alternate double bonds and shows a resonance structure due to delocalization of pi electrons in it. The resonance makes benzene more stable than the compound having 3 separate double bonds.